In this video, I'm going to be talking to you about some elementary derivative rules, the power rule, derivatives of sine and cosine, and getting started on some good old-fashioned like derivative calculus problems. So remember last time we talked about the derivative, and we defined it as f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. It's the limit of rise over run as run goes towards 0. The meaning was the slope of the tangent line it was also the instantaneous rate of change. And notationally, how we, talked about the derivative was, if we started with a function f of x and then we went and took the derivative of it, we were getting f prime of x. Okay, if we started with y and we took the derivative of it, we are getting dy dx. Now, I may have failed to mention last time that we can also say y prime. And what I want to tell you right now is, this is notation I'll be using today in this video and throughout the course, is that when I talk about, d dx of something, that's an operator, kind of like sine or natural log or square root. It's something, except this is something that we do to a function, right? We take the derivative of a function. So I just want to point that out, that this means take derivative of whatever's inside the brackets with respect to x. All right. Now let's get into it and kind of build up the power rule. So last time we showed that the derivative of a number times x was just that number, because it was the derivative is the slope, and a number times x is a line with slope that number. The derivative with respect to x of x squared is 2x. I showed you that using the limit definition of the derivative and some algebra tricks. And then the derivative of a number, of a constant a, is going to be 0, because it's constant, it's not changing, and the derivative is rate of change. Okay. So I'm going to consider the graph of f of x as x times x plus 4 times x minus 4. Okay, so I'm just going to draw you a quick sketch. I think for our purposes, that's going to do just fine. Okay, I think I want it to, maybe my axis to be a little bit, yeah, so that looks like you're pretty evenly spaced. And so I'm going to say that this is -4, this is 0, and that's going to be 4. Okay. Now, I am going to sketch, what I'm doing here is I'm planning on sketching the derivative of f. So this is the graph of f, and I'm going to sketch the graph. And then hopefully we'll notice a pattern here. So first, when I'm sketching the graphs of these derivatives, I like to start with the flat spots, right? Where is the tangent horizontal? Get stolen shot. Okay, so I track back to here, and we know it's somewhere between 0 and 4, but we do not know that that's 2. Okay, we don't really have the tools yet. Very soon we'll have the tools to deal with that. Okay, so I'm going to go over here. I am going to mark off 0 to kind of give myself like an anchor. But then I'm just going to kind of mark off these red spots that I know they aren't at 2, but maybe you don't know that yet. Yeah. So, hold on. What am I? Oh, since I've got slope equals 0, that means f prime has to equal 0. Okay. So on the graph of f prime, these are x-intercepts. Okay. Now, next, I like to find places where the slope is positive. Okay, here, positive slope, positive slope, positive slope. So f prime is positive. Okay. So I need to be positive over here, to the left of my first flat spot. And then to the right of my second flat spot, right, I've got positive slopes of tangent lines. Okay, so it needs to be positive out here. Okay. And in the middle, between my two flat spots, I'm seeing negative slopes. Right. That. And so I just need to make sure that it's, kind of negative down in here. And, well, at this point, we don't really know that much about the shape of these things, so I'm just going to take a guess at drawing something that goes from positive to 0 to negative back to positive. And what do you know? That does look like a parabola, right? A parabola does fit this description. And so this is f prime. Okay, so notice over here, let me grab a different color. That over here, the derivative of a first-degree polynomial was a number, which is a zero-degree polynomial. Over here, the derivative of a second-degree polynomial was equal to a first-degree polynomial. Okay. And now we're seeing that the derivative of a third-degree polynomial is looking very much like a second-degree polynomial. So it seems taking the derivative is going to knock down the power of our polynomial by 1 degree. And indeed, this is the power rule. So if we have any power of x, any real number power of x, then the derivative of that is going to be the power times x to the 1 less power. So it's n times x to the n minus 1. And this is going to be a really, really important formula for us throughout the whole year. All right, so let's get to work on some examples. We're going to start with x to the 5. Yeah, this is a good one to start with. Okay, so that means, lost the rule. So this means that f prime of x is going to be, we take the power, we bring it down into the front, and we decrease the power by 1. It's 5x to the 4. Okay? But what about this 4 times x to the 5? You know, I think next time we're going to see that products of two functions can cause some difficulty with taking the derivative. Is it a big deal that we've changed this by multiplying by 4, or is it just going to multiply the derivative by 4? And so that's kind of one of our first derivative properties, is that it is okay to multiply by a constant, right? The derivative of a number times a function is that number times the derivative of the function, just provided that we're multiplying by a number and not some other function involving x. That's a big distinction there. Meaning that g prime of x, I'm going to do the exact same thing. I'm going to bring this 5 down, I'm going to multiply it by the 4, and I'm going to get 20x to the 4. Okay? Now the next two are kind of ones that, tricky power rule examples that I just have to jump out in front of them and show you right now. We need to rewrite these as a power of. But I know that y'all know that y equals 1 over x is the same as y equals x to the negative 1, and y equals square root of x is equal to y equals x to the 1 half. That's the same thing, right? So I can find these derivatives. I can say dy dx, pardon me. In this case, dy dx, I'm just going to apply the power rule. I'm going to say that's negative 1 times x. It's supposed to be a parenthesis, didn't really look like it. And I'm going to subtract 1 from the power, right? It's n times x to the n minus 1. Okay? It is one less in the sense that we are subtracting 1, so it's even more negative. And then over here, okay, I've got, and I was going to mention that you can write this as negative 1 over x squared if you like, but if you want to just call it negative x to the negative 2, that's completely fine. Same function. And y equals x to the 1 half, if I go to take the derivative of that, I'm going to use the power rule, and I'm going to get 1 half times x to 1 half. And because I decrease the power by 1, and 1 half minus 1, or 1 half minus 2 halves is negative 1. Oh, and then before I move on, you see that, like, maybe if you're looking at the notes packet yourself, you'll see that the next example is kind of like a polynomial. It's like, what happens when we add multiple functions together and we want to take the derivative? And so, again, the derivative of the sum is the sum of the derivatives, provided that these derivatives exist in the first place, right? If g is not a differentiable function, then f plus g is not going to become suddenly a differentiable function, right? You can't add a real number to something that doesn't exist. All right, so here we've got ourselves a nice little polynomial. And I think first I would ask you to, find the derivative of f. So we'll say that f prime of x, we will apply our brand new power rule. The derivative of x to the 3 is going to be 3 times x to the 2. And then minus x, okay, well, the derivative of a number times x is just that number, so that's going to be minus 1. And then the derivative of 2 is equal to 0. And now I won't always write the plus 0 to remind you that the derivative of 2 is equal to 0, but I feel like, when we're just getting started, I'm going to do that for a while. All right, so next they want us to write an equation for the line tangent to the graph of f at x equals negative 2. And hold on. Yes, I did show you how to do this in the last video, how to write an equation for a tangent line, so I'm not going to go in and talk so much about this. You know that you're going to need a point. And we can get a point using x equals negative 2 and y is equal to f of negative 2. Okay? Now I am going to need to go over and figure out what f of negative 2 is. And it's been a few days since I've delivered this lesson, so it's negative 2 to the 3, which is negative 8, minus negative 2 plus 2. So I'm adding 4 to negative 8, and that's negative 4. Yeah, that seems familiar. So my point is going to be negative 2 and negative 4. Then my slope, well, I need to figure out what is f prime of negative 2. That's going to be equal to 3 times negative 2 squared minus 1. So 3 times 4 is 12 minus 1 is 11. So I've got a slope of 11, and then I can write the equation of my tangent line. I'll say that's y minus the y coordinate we know, y minus negative 4 is equal to this given by f prime times x minus the x coordinate that we know. All right. All right. Now let's talk about some transcendental functions. Okay, and that might be a word or terminology you've not heard in the past. But in this class, which I don't think you really need to know which of the functions are transcendental, I'm just going to tell you that the ones that we're going to be dealing with are going to be, exponential, trigonometric, and what's the other one? Oh, logarithmic. They are not, basically the hallmark of a transcendental function is not algebraic. We can't express it in terms of normal arithmetic operations like addition, subtraction, multiplication, division, or algebraic operations like squaring, square rooting, things like that. Okay. And so at this point, I'm just going to be telling you the derivatives of these things. So that the derivative of sine of x is equal to cosine x. The derivative of cosine of x is equal to negative sine of x. The derivative of e to the x is e to the x. And the derivative of natural log of x, which if you ever hear me talk about log of x, I mean natural log. Okay, the derivative of log of x is 1 over x. Okay. Now, I am not going to prove any of these formulas to you right now because to do any of them would make this video way too long. I'm going to just focus on working examples. But if you are interested, the proofs of these formulas are right at your level, okay? Right at your introductory first-time calculus student level. So those are available on the YouTube channel. They'll definitely be linked in the description of this video, right? And the proof of the power rule too, I'm going to put in the description of the video. So, just if you're interested in why any of these things are true, you might need to go and do some more video watching, but I have all of that available to you. But for now, I need you to know that the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of e to the x is e to the x, and the derivative of natural log of x is 1 over x. Those are formulas that we just have to know in this class. And as much as I would like to, sit y'all down and go through the graph of y equals sine x and the graph of y equals cosine x and graph the derivatives and show you evidence of why, those formulas are true, or, go in with a calculator and look at the graphs of e to the x and natural log of x and look at why those formulas are true. I just don't think that that's the best use of our time together, since we're only together every other day. I think that we need to just kind of move forward and get to the point where we can work through examples. So, keeping with that, write an equation for the line tangent to the graph of y equals 5 cosine x at x equals pi over 3. All right, we can do this. So, let's start with getting a point. So the point is going to be x equals pi over 3, and y is going to be 5 times the cosine of pi over 3. Okay? And maybe you're like, kind of forgetting how to find the cosine of pi over 3. Okay, you know that pi over 3 is less than 1 pi, so it has to be up here. Okay? We know that pi over 2, if this is pi over 2. And so pi over 3 is less than pi over 2, so it's got to be in the first quadrant. Right? That's kind of the first elimination. And second of all, you got to know that these pi over 3s, those correspond to the really tall triangles, to the 60-degree reference angle, right? So we're talking about this triangle right here. And that's supposed to be a right triangle. And we know that on the unit circle, all of the triangles have hypotenuse 1. And maybe this isn't even the best, it's in the best drawing. Maybe I'll draw it a little more tall and exaggerated. Yeah, that's a little better. All the triangles on the unit circle have hypotenuse 1. And we know that for a 30, 60, 90 triangle, the short leg is a half, the long leg is root 3 over 2. And of course, that is because the square root of 3 is a bigger number than 1. What do you think about that? Now, if we're trying to find the cosine of pi over 3, I'm going to do SOHCAHTOA, cosine adjacent over hypotenuse. That's 1/2 divided by 1, so 5 times a half. So pi over 3 and 5/2. Then I'll need a slope. Okay, y equals 5 cosine x. We're going to need the derivative. So that's dy dx equals 5 times the derivative of cosine is negative sine. So that's negative 5 sine x. Okay. Then I'm going to need dy dx at the point where x is equal to pi over 3. That's going to be, well, negative 5 times the sine of pi over 3. Luckily for us, I've got the diagram over there. Sine, SOHCAHTOA, opposite over hypotenuse. That's root 3 over 2. So that's negative 5 times root 3 divided by 2. So now I'm ready to write my equation. And that's going to be y minus the y-coordinate of the point we know on the line is equal to the slope times x minus the x-coordinate of the point we know on the line. All right, and then we're good here. It's definitely a safe place to stop, but I think that this is also a good example of why it's maybe not the best idea ever to try to distribute the slope and write it as y equals mx plus b. It isn't really going to guarantee you you're any better off. Okay? So I recommend just staying in point slope form. All right. Here we've got another example, write an equation for the line normal to the graph of h of x equals 2 natural log x. I don't remember if I have actually told you about the normal line yet in these videos or not, so I'm just going to really quickly define it up here. Yeah. And I'll just kind of pause and then. So a normal line is perpendicular to the tangent line at the point of tangency. So how we're going to find a normal line, it's going to be exactly the same as how we find a tangent line. We're just going to switch up the slope at the end in a way that you used to do when you were in Algebra 1. So you know how to do this, is what I'm saying. So we're going to start off with getting a point. And the point is going to be x equals e, and y is going to be h of e. So that's going to be 2 times the natural log of e. Okay. Feeling like, based on how things I've seen so far, I feel like we might need some help unpackaging this. Okay, at this point in the year. So remember that natural log of e or really, hold on, let me just start with the natural log of a number is equal to the special exponent I put on e, right? Like it's log with base e. So it's the special exponent I put on e to get that number. And maybe it's, I should think of that. I should say, I think, what is the special exponent I put on e to get that number? So if I switch this up to natural log of e, man, I can't keep this thing anchored. Natural log of e, it's like, what is the special exponent I put on e to get e? And it's going to be just the one exponent, right? So I'm going to conclude that natural log of e is 1, and I'm going to try to get this back in my shot again. And so I'll know that the point is e and 2, is what I'm saying. The slope I will get by taking the derivative. Okay, I need h prime of x. That's equal to 2 times the derivative of natural log of x. Okay, and the derivative of natural log is 1 over x, so that's 2 times 1 over x, which you could leave like that, or you could write it as 2 over x. Then I'll need h prime at the point where x is equal to e to get my slope of my tangent line. And that's 2 divided by e. Okay. So now I'm ready to write my equation. And that's going to be y minus 2 equals, wait a second, I forgot that I'm not writing the equation of a tangent line. I'm writing an equation of a normal line. So the perpendicular slope, and I know it's been a long time for most of y'all, since Algebra 1 or thinking about perpendicular lines, but perpendicular lines, I remember how we said it when I taught college algebra, was we said that the slopes of perpendicular lines, if you multiply them, you get -1 every time. Okay, you might have said that they are negative reciprocals or opposite reciprocals or something like that. What you do, you take the slope, if it's a fraction, you flip it, you make it negative. So that's going to be negative e divided by 2. So y minus 2 is going to be perpendicular slope x minus the x coordinate we know. Okay, and that's how we write the equation of a normal line. Now I'm going to talk to you about some higher order derivatives. Okay, so like the derivative of the derivative. Okay, the derivative of a derivative can definitely give us really useful information, and we'll be interested in well, that information it can give us about the original function, and we'll be looking at that really in the next unit. But for now, I just need to tell you about. So if we've got a derivative, dy dx, and we go to take the derivative of it, right, take the derivative of dy dx, then we'll get the second derivative of y with respect to x both times, where that's a very loose interpretation of what exponents mean. But this means the second derivative. Okay? And if I go to take the derivative of x, right, if I had f prime of x prime, we're just going to call that f double prime of x. And we would call these the second derivative. Now, the second derivative is not the only derivative we're interested in addition to the first derivative, right? We can be interested in the third derivative, like, f triple prime, or the third derivative of y with respect to x all 3 times. But as far as the primes or the tick marks near the f goes, after 3, probably too much to count, or just to look at. So the way we do that is we would usually put like a parenthesis in there. So f's fourth derivative, the fourth derivative of y with respect to x all 4 times, or, later on, higher order, nth order derivative, it will be just f's nth derivative, the nth derivative of y on x all n times. You keep going in calculus, you go to a multivariable calculus class, you might not take the derivative with respect to the same variable each time because there's multiple variables, and so that's where, that kind of comes in. But in this class, we'll never take the derivative of a derivative with respect to a different variable that we started on. That just won't happen in this class. That's different situation. All right. So these are a couple other things that I need to just, make you aware of before I set you loose on all these problems. And these are some, algebraic things that can happen that make us, a little confused on the derivative taking front, but it actually won't hurt us, okay? So actually, I'm going to need to move that second derivative way down, because in order to get the second derivative, I have to write the first derivative first. And I'm not even ready to write the first derivative, right? Because we don't have a way to deal with 2x plus 5 times 2x plus 5, or the way to deal with composite functions. You're just going to need to, keep showing up or keep watching these videos, and I'll show you how to deal with that. For now, the only thing that we can do is say that this is 2x plus 5 times 2x plus 5, and actually distribute and write this as y equals 4x squared plus 10 20x plus 25, right? Then we can take the derivative and say that dy dx is equal to, use the power rule, 2 times 4 is 8x to the first power plus 20, because the derivative of a number times x is just a number, plus 0, because the derivative of 25 is 0. Then I can take the derivative of that and get the second derivative of y with respect to x both times is going to be, well, the derivative of 8x is 8, the derivative of 20 is 0, and the derivative of 0 is also 0. So that's equal to 8. Okay. Now, over here, we're definitely not ready to find f triple prime of x. That's going to have to come way down here. I'm not sure what I was thinking when I put that right underneath. But with this, we're not ready. We don't have any tools to deal with fractions, right? We can't take the derivative of a quotient yet. That's in the next video. Okay? So what we need to do is we need to actually use the distributive property again. And so I'm going to call this, 1 over 4x squared times x to the third plus 2x to the 2 plus 3x to the 1. Okay, and so I'm going to rewrite f of x as, all right, so I take that 1 over 4x squared and I multiply it by the x to the 3, and I'll have x to the 3 divided by x to the 2 is x to the 1. So that's 1/4 of x to the 1 power. Then I'll have 2x to the 2 divided by 4x to the 2 is going to be 2/4. And then when I have 3x divided by 4x squared, well, as far as the numbers go, I'll have 3/4. And, knowing what we know about that property of constant multiples of functions, taking their derivatives, I'm just going to take the number and just hold it out front. So I can just take the derivative separately and not worry about all the numbers. But then when I have x divided by x to the 2, that's like 1 over x, right? That's an extra copy of x in the denominator. But I know from earlier that 1 over x, again, I'm going to have to rewrite that as x to the negative 1 eventually, so I might as well just start with it right now. So first derivative, f prime, derivative of 1/4 x is 1/4, derivative of 1/2 is 0, and then I'll have minus 3/4 x to the negative 2. Then when I take the second derivative, I'll have the derivative of 1/4 plus 0. Well, the derivative of 1/4, that's 0. So I'll have 0 plus, because minus 2 times negative 3/4 is going to be positive 6 over 4 x to the negative 3. Yeah. And then when I go to take the derivative one more time to get f triple prime, I'm going to have negative 18 over 4 times x to the negative 4. And of course, there's all sorts of different ways you could write that. You could reduce that fraction, you could throw that x to the 4 in the denominator, or you could just leave it just like that. All right, here's 2 more examples, and I think I want you to try these, and yeah, give these a shot on your own. So pause the video right now, and then when you unpause it, the answers are just going to pop up in a few seconds. All right, there you go. Okay, I'm just really in the red, I was using the power rule and the derivatives of sine and cosine, and then on the right, okay, you need to know that the derivative of natural log of x is 1 over x, and then you need to know that if you have to take the derivative of that, you need to read 1, and then I was just using the product rule from there. All right, I do have some more examples in my note packet, but I'm seeing that my video has just gone over 30 minutes, and so I'm going to try to go through these really fast, but I wouldn't want anybody to feel like, I've given you examples and not showing you how to do them. So first, we're going to talk about horizontal tangent problem. Okay, horizontal tangent line, we know that that's code for derivative equals 0. So we want the solutions to f prime of x equals 0. Using the power rule, I can see that I've got f prime of x equals 2x minus 8, because the derivative of 5 is 0, and the derivative of a number times x is that number, and the derivative of x squared is 2x. Okay, and if I want to know where f prime of x equals 0, I'm going to, kind of combine these things. I'm going to say, well, that means that 2x minus 8 needs to equal 0, meaning that x equals 4 is a place where f of x has a horizontal tangent line. If you needed the equation of the tangent line itself, well, you'd need the y-coordinate, right? Because a horizontal line is just y equals some number. And in this case, it looks like it would be 16 minus 32 is negative 16, plus 5 is negative 11, y equals negative 11. Say the xy coordinate would be 4 and negative 11, whatever you want. All right, this one is a very common AP multiple choice question. I've got a bunch of versions of this question. Find the values of a and b so that g is differentiable at x equals 2. And it looks like I meant to use capital A and capital B so that nobody got confused between lowercase b and 6. All right, so if these things are going to be differentiable, not only do we need them to be meeting up at a point, right? This is not good enough. We need that meetup to be smooth. So maybe it needs to be like, and then we fill in here, and it goes on like that, and even that didn't look all that smooth, but it's supposed to be. Okay, so how we're going to do that is we need the same value of y, and that's where we're going to set ax to the 3 equal to x squared plus b at x equals 2. We'll also need to say that they have the same slope, these two pieces. The same, maybe I'll call it y prime. Okay. But okay, we need to go over here and kind of take the derivative of g. Okay, so if we've got a piecewise function, in general, if we want to take the derivative of it, we just take the derivative of the pieces. So that's 3ax squared, because a is just a number. And now we will generally lose our, our endpoints, but we're actually working to make sure that this is differentiable at x equals 2. I don't know why I said 0. So, eventually these things will be the same, and so you would kind of put that back on there, I guess. But, and then the derivative of this is 2x when x is greater than 2. I got to point out, if we didn't go in and make sure that these slopes were equal to each other, then we would not have x equals 2 in the 3ax squared part of the piecewise defined g prime. All right, so I've taken the derivatives. I'm happy. I'm going to say that 3ax squared needs to equal 2x at x equals 2. Okay. Well, let's plug in x equals 2. So a times 2 to the third is 8a is equal to 2 squared is 4 plus b. That does not help me all that much. I mean, it's good, but I still need more information to pin this down. So I'm going to plug in on x equals 2 over here, and I'll get 3 times a times 4 is 12a equals 2x is 4. So a is seeming like 4/12. Oh no. Okay, whatever. Now, 8a is 8/3 equals 4 plus b. So I'm going to say 8/3 minus 4 is what b is. B is 12/3, so it seems to me like b is going to need to be negative 4/3. 8 minus 12 is negative 4, yeah. Okay, and that's how we determined values of a and b that made the function differentiable at x equals 2. Now let's talk about finding x locations where the line tangent to the graph of f of x equals x to the 3 minus 3x to the 2 is parallel to the line y equals 9x minus 2. Okay, we can do that. I just want you to remember that parallel lines have equal slopes. That's important. And so if the line tangent is parallel to y equals 9x minus 2, that means that the slope of the tangent line needs to equal 9, meaning that f prime of, x, it needs to equal 9. I'm not sure what I said earlier. Oh, I didn't say that right. All right. But, okay, I've got over here f prime of x is equal to 3x squared minus 6x. I want that to equal 9. And if I've got a polynomial that's degree higher than 1, I have to set it equal to 0 in order to solve it. Because either I'm going to be able to set it equal to 0 and factor it, or I'm going to have to set it equal to 0 and use technology to solve it. Either way, we're going to set it equal to 0 in this class to solve polynomials higher than degree 1. So 3x squared minus 6x minus 9 is equal to 0. Okay, I'm going to factor out the 3, and I'll have x squared minus 2x minus 3 equals 0. That does look factorable. Okay, so that's 3 times x minus 3 times x plus 1 equals 0. Yes, and I'll say that if these three things multiply to be equal to 0, one of them has to be 0, right? So either 3 equals 0, which is not really possible, or x minus 3 equals 0. That does feel possible, right? That would be if x was equal to 3. Or if x was equal to negative 1, because x plus 1 equals 0. Okay? So those are the x locations where the line tangent to the graph of f is parallel to the line y equals 9x minus 2. All right, and then the last one I've got for you is find the value of k that makes the line y equals 4x minus 9 actually sit tangent to the graph, not just parallel to the tangent on the graph of f. Okay, we need to actually find where it meets up. So much like the piecewise function example, we need to, set some things equal to each other, on a y level and on a y prime level. Okay, so we need them to have the same y. So y and f of x need to be the same at the place that they share. So I need 4x minus 9 to equal x squared minus kx. But I don't know the x coordinate of where this is going to happen, right? I don't know where that's happening. So what I need to also consider is that these things need to have the same slope. So the line has slope 4. So I need 4 to equal 2x minus k, right? Because that's the derivative of f of x. It's going to be 2x minus k. So I need 2x minus k equals 4. It's like, oh man, what am I going to do here? This isn't a linear system. I'm not just going to be able to use substitution or elimination. And my advice to you with a nonlinear system is you just do the best you can, right? Substitution is oftentimes a good way to go. So what I'm going to do is I'm going to solve for, I've got an idea. Okay, I see 2x here and I see 4x there. I'm going to get 4x over here on the right side. So I'm going to say 4x minus 2k equals 8. I'm going to solve for it. So 4x equals, whoops, that's not going to be good enough. Okay, hopefully you see why. Hopefully we're watching this right, dude, that's a bad idea. It's a bad idea. Please don't. Please stop. Realize you're doing a bad thing soon. I just realized if I solve for 4x, I'll still have that x squared and that kx, and that won't actually do any good. What I want to do is get rid of this k so I have it down in one variable. Embarrassing. So, but it's all right. I just saw the 2x and 4x, got too excited. So k is going to be equal to 2x minus 4. Okay, because I didn't want to distribute in the x, but that was just being lazy, right? So 4x minus 9 equals x squared minus 2x minus 4 times x. Oh, interesting. Hold on. minus 2x squared, this is going to be a plus 4x. And, okay, yeah, now I'm going to set it equal to 0, so I've got x squared minus 2x squared is negative x squared, so I'll put that over here. X squared, oh, 4x minus 4x, that's convenient. Oh, okay. So I've got x equals 3, or perhaps x equals negative 3. That's interesting. I was kind of expecting to just come back with 1. But let's see. Okay, k equals 2x minus 4. Oh, this is interesting. So it appears that k could be 6 minus 4 is 2. Or it's possible that k could be negative 6 minus 4 is negative 10. And it looks like if that's the case, then I have x squared minus 3x. Why would 4x minus 9? Hold on, I'm just going to... Huh, that's interesting. Yeah, I can see why that would cause two different parabolas to kind of fit that. But I'll let you think about why that's the case. And that's all the examples I got for you. This has been a good, decently long video, but this is really us getting started on our derivative taking and really good calculus stuff. So you definitely need to practice this stuff. I've got lots of example problems for you to work on, and you'll just let me know if you need any support with that.